Hey guys, in this episode we're going to talk about bit banging. Old school cool bit banging. Stay tuned. Let's say that you got a microprocessor, doesn't have a UART, you've got no hardware, and you need to talk to another device. You're going to talk through a serial interface. There's a number of options that are available, especially if you have control on both sides. However, there are times when you need to talk a specific protocol, like a serial protocol, and you don't have a UART. So you're going to have to write it in software. That's what bit banging is. You're going to have to handle all the timing yourself in the software. So let me pull up a whiteboard and I will show you how you go about calculating the timings and what the details of this whole process involve. And then we'll actually look at some old 6502 source code for a project that you'll be seeing in the future where I had to implement this exact same process, bit banging. All right, so on the whiteboard, what I've got is this SpeakJet IC. It has a serial interface, and for the project I was working on, I wanted to interface an Atari 800XL, which has a 6502 microprocessor in it, serially to the SpeakJet. If we look at this text here, this is from the SpeakJet datasheet. You'll see that it talks about the serial input provides a way to communicate with it. It talks about it being logic levels, which means TTL voltages, not RS-232 voltages. RS-232 typically is like 12, positive 12, minus 12. TTL is going to be 5 volts, 0 to 5. So I wanted the 6502 to be able to talk to this chip through a serial interface. In fact, pretty much the same serial interface you would use if your Arduino wanted to talk to the serial monitor in the Arduino IDE. If you remember, in that IDE, you choose the baud rate, and I believe it's a no parity, one stop bit. What does that mean? What does 9600 baud mean, for example, and no parity, one stop bit? Well, you're going to have to know what that is because you're going to have to write it in software. So let's take a look real quick at an RS-232 data packet, a data frame. I grabbed this off Wikipedia under the RS-232 page. So if we look at this, this is talking real RS-232. That's why the voltages you see here are plus 15 to minus 15. Also notice that it looks like a 1, a bit 1 is actually inverse, and that's also true, that they are actually the inverse of what you would expect. So let's look at this real quick. We're going to send 11010010. We're going to send that to a serial interface. So we have this thing in the front called a start, we got this thing in the back called a stop, and we're sending it least significant bit to most significant bit. Now remember, in my example, I'm using TTL voltages as per the data spec. So my voltages will be 0 to 5 volts. So the very first thing you do is you send a start bit in RS-232, and the start bit goes high, and then we're going to send the 8 bits of our data, in this case 1, so we go to 0 or less than 0, 1, and then 0 goes high, 1 goes low, 0, 0 is 2 highs, a low, a high, and then we have a stop bit. So the key to all of this is, in bit banging, is really it's all about the timing. How long do you send each of these pieces of data? How long do you send the start? How long do you send a 1? How long do you send a 0? How long do you send a stop? And fortunately, that's fairly easy to calculate. If we look over here, and by the way, why we need to know that is because we're going to have to implement those delays in the software. We need to send a 1 and then wait. And there's lots of ways to do that. But let's first take a look at the times that we're talking about here. If I'm going to do this at 9600 baud, which I am because that's the default serial communication speed for the SpeakJet IC, I'm going to take 1 over 9600 baud, and with a little bit of math, I see that each bit needs to be sent at 104.2 microseconds. So that's the timing that needs to be implemented to do a 9600 baud rate. Now, if we determine what our processor is, we can then determine what our cycle times are. So what are cycle times? Well, let's look at something really quick. On a 6502, when we talk cycle times, we're talking about how long does it take for an instruction to execute. So they use the term cycles. So an AND here in this example, an AND is 2 cycles. If it's going to be an indirect, it's 6, and you know what each of these instructions represents. If we look at like the 8086 here, you'll see that here's 8 cycles. The instruction is 1 byte, 8 cycles, 4 cycles, depending on Pentium, 3 cycles, 486, 3 cycles. So what does that equate to? What is a cycle? Well, that's where you go back to this calculation. How fast is the microprocessor running? In this case, my Atari 800XL is running at 1.79 megahertz, which means that 1 cycle equals 0.559 microseconds. So now that I know how long each cycle is, and I know how long I need to be able to hold each of the bits in the data frame, I can figure out in software now how long to hold these and how much time it takes, and I can even make adjustments for different baud rates. Now, you're saying, this is old school stuff. It definitely is old school stuff. It still has an impact today in a number of cases. One of the things you need to look out for, though, is depending on the microprocessor. Most microprocessors are extremely fast today, extremely fast, and they have pipelines. And when you look at pipelines and determining cycle times, there can be a number of changes to the clock times for those instructions, depending upon a number of things like prefetch queues, all sorts of stuff. So it's very hard to calculate. However, you will have an advantage because by the time if you're using those kind of processors to implement bit banging, you probably will already have very accurate delay timers at the microsecond level. So you won't have to do what I have to do on the 6502. You'll just call the delay function after you understand what your main code is running at. You'll call a delay for maybe 104 microseconds, let's say, if you're going 9600 baud, or maybe a little bit less than that because the instructions above it took some time. So you can kind of tweak this delay number so that you can get the proper speed. And that's part of your testing scenario anyway. So knowing how I'm doing this with the Atari 800XL, let's go ahead and take a look at an example of this working, and then we'll take a look at the 6502 assembly language. All right, let me explain to you what you're seeing here. You're seeing this ESP Atari bridge code back here in the back. We're seeing the serial monitor that comes with the Arduino IDE, and this is the screen from my Atari 800 XL running the Max 65 assembler. So what I have done to simplify the interface for the demonstration is I am using the ESP8266 simply as a bridge. I have serial output coming from the Atari 800's joystick port. The XL has 2 ports, and you can actually convert them for output as well as for input. So I'm using one of them to write the bits out to the ESP8266, which is going to read them and then output them itself. So it's really simple. We're using a software serial interface. i.e. a bit banging software serial interface that someone else wrote, so that I can have two serial interfaces. One, the one that's normal and built in so that we can see the monitor. And then we're also going to read in what the Atari is sending us. And basically all we do is look for the inputs from the Atari and we write them back out again. So with that, I've got the ESP8266. I'm going to hit restart on it. And it comes up and says start banging those bits, which is this string here. Now if we go over to the Atari and I assemble the code and I go into DDT to run it, and I'm going to tell it to start at 4000 hex. This interface allows me to type and send the data that I type over serial to the ESP, which should then show it on our monitor. So if I type hello and press enter, we get the word hello in the serial monitor. So the Atari is actually sending at 9600 baud the binary data to the ESP8266, which is expecting to read at 9600 baud, and then it's outputting the data itself at 9600 baud. Of course, we could change any of these speeds. You know, there could be a different speed between the ESP and the Atari, and a different speed between the ESP and the serial monitor. They just happen to both be 9600 baud. So as you can see, through assembly language on the 6502, I am bit banging. I am creating a serial interface which is compatible with the serial interface on both the monitor as well as, you know, the ESP's software serial interface that I'm using. So with that, now let's go and take a look at the 6502 code and see how the timing works, because that's really the heart of this. All right, I have ported the bit bang assembly language from my Atari 800XL onto my Windows machine so you can more easily see it. I'm not going to go through every line. This is going to be kind of a quick review until we get to the section that really has to do with bit banging and the timing of the bit banging. So we've got some equates here. These are just standard defines. This is me setting up a joystick port so that I can output to it. Then we're setting up a buffer here. So as you type in, it goes into the buffer. We get a character, we send it to the screen, we put it in the buffer. If the user hits the enter key, then we want to send that buffer. If they hit the backspace key, we want to back the buffer up a character so that we can overwrite things. When you hit enter, we call send out. So we're getting ready to send this buffer out the serial port, or the joystick port in this case. What that really does is, let's see. Yep, gets it set up and we'll go and calls write buffer basically. So when we call write buffer, what we're really going to do here is we are going to reset a few things and then call write byte. Oh, what we're doing is we're looping over the buffer, looking to see for the null, looking for a null. When we find the null, we know we're done. Otherwise, we send each byte out. Okay, so write byte is really part of the heart of this whole thing. Every byte that gets written out to the serial port comes through this routine. So when you think about that data frame we looked at for RS-232, this is basically the start of that data frame. It is. In fact, the first bit of code here is just making sure that we're ready to send. It's a little bit of flow control. There's lots of different kinds of flow control, but the theory is that the device you're sending to can tell you, hey, hold up, slow down, I need you to wait, and this allows for that. The next section is we're ready to go now, so we're going to send a bit, and we send a start bit. If you think about that data frame, the first thing we do is send a start bit. Then the heart right here is now we have to call baud wait. How long do we wait? We saw the calculations for that. So we'll look at that baud wait function, which is really the heart of all of the timing. The next thing we need to do is there's going to be 8 bits in a byte, and this is going to basically go through and take each bit from the least significant bit to the most significant and basically shift it out and AND it, so we only ended up with 1 bit, and send it out the port and call wait for each bit. Boom, 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 zeros and ones. When that's done, we call the stop bit. We call another wait, and we re-enable interrupts. We disabled interrupts somewhere up here at the top. So to try to get the timing, if you're not familiar, you have interrupts, non-maskable and maskable interrupts. In most systems, non-maskable you can't do much with. Those are going to be very highly important, prioritized interrupts needed by the system. Maskable interrupts, or interrupts you can stop, you can basically turn off so that they don't impact what you're doing. And that's what we needed to do in this case because we wanted our timings to be fairly accurate. This is the routine to set up the joystick for output. Okay, and then this is what we just talked about when we looked at the math. I put some comments in here for the calculation. This is the baud wait. So every time that we send something out, we call baud wait, and then when baud wait returns, we can then go to the next one, next bit, or next stop bit, or whatever it might be. So as you can see, every one of these instructions, I calculated the number of cycles. So we have 10 cycles in this pre-loop. Then here's a no-op, and this is basically a loop. And in this loop, it basically is telling you 7 cycles in loop, 7 times. This is the per cycle time. That tells you how many cycles, and then 16 cycles post-loop. So using these numbers now, you can calculate that this routine takes 18.44 microseconds to execute. And you can then determine how much time, how many loops you need to make at this timing, if you will, this number of microseconds, to make sure that you meet that 104 microsecond delay needed for 9600 baud. And if we go back to the top just real quick, that's what these numbers are right here. So 16 times through that loop or 4 times through that loop, depending upon what speed. 9600 baud, you got to go 16 times through that loop. So it was 16 and 4. I might have said 6. I didn't mean to. 16 or 4. And that's it. That's this whole thing. There's a couple other routines here. So that's how you bit bang something. You need to provide your own timings. And in the case of an Atari 800, a 6502 microprocessor, without, well, at the speeds they're at, 1.79 megahertz, that's not a very fast computer in today's world. If you want to do bit banging, this is pretty much how you want to do it. You want to calculate your instruction timings so that you can meet the requirement. Now, as I kind of hinted at before, if you're using a modern controller, let's say you're using an ESP8266, but for some reason you don't have a UART. That one has a UART. But let's play like you've got this controller, it's modern, doesn't have a UART on it, and you're going to have to do some bit banging. The things to consider are, if you have a microsecond timer, then chances are you can use the microsecond timer instead of writing your own baud wait type function. You can actually just call that. You could use a profiler to take a look at how long your write bit routine is taking. So the code to actually write the bit, how long does that take? Then what do I really need to wait afterwards for the next bit? And you can probably get away with some type of delay-like function. If not, you can also look at things like interrupt-driven code to do the writes. You could write into a buffer and then have an interrupt fire based on a timer to pick up each bit or each byte, so you're not actually wasting time. This is wasting time. That's what's going on. And typically that's not a good thing. Other things can't happen when you're wasting time. So an interrupt driven solution would even be better. All right, well, you've seen some old school bit banging. Hopefully you've learned something interesting. I hope you have. I'm being plagued by cat hair. Nevertheless, remember, learn something new every day, or something like that.